Okay, good morning. Let's get started. So we were looking at two-dimensional diffusion equation and the boundary conditions, right, in the last lecture. So we are looking at two-dimensional steady diffusion equation, and in that context we are looking at the boundary conditions. All right. So we have finished discussion on Dirichlet boundary condition and also on Neumann boundary condition, right. The only one that is remaining is the discussion on mixed boundary condition where we specify a kind of proportionate amounts or a linear combination of a Dirichlet and a Neumann, right. We are going to specify a times the dependent variable phi plus some b times partial phi partial n equals some c, right. So this will be a combination of Dirichlet and a gradient boundary conditions. We said one of the examples for having a mixed boundary condition is convection, right. So for example, if we have so I'm going to just go to next page and the convection. So essentially if we have a fluid that is moving at certain velocity with the temperature of the fluid being phi infinity or the scalar being phi infinity, and if h being the heat transfer coefficient, then we said we can have a mixed boundary condition, and if we discretize the near boundary cells as this. So if we have P, E and north and south, okay, and the excuse me, so and the cell widths, that is delta x delta y, remain the same as before, and then we also have these distances. Those are delta x E between the P cell and the east cell, and delta x B between the boundary and the P cell, right. So we have these distances. So we have del x E, del x B, delta y north and delta y south, okay. So these are denoted as before, delta y north and then delta y south, okay. So these are there. Now coming to the specification of the boundary condition, what we have is, if let us say the temperature on the boundary is phi b, okay, then a convection would read the heat flux that is coming in, let us say if we call it Q, then it will be minus gamma grad phi on the boundary dotted with I, right, that is the heat flux in the positive x direction, would be equal to what? Would be equal to the convection heat transfer, right. So this is h times phi infinity minus phi b, right. So that's what we have. So essentially this is a mixed boundary condition, right. So if we look at, if you write this, rewrite this thing, this will be gamma b partial phi partial x b equals h times phi infinity minus phi b. So we essentially have a combination of the Dirichlet and a Neumann adding up to some constant here. So we have a phi plus b partial phi partial n equal to constant, okay. So that's kind of boundary condition. Now of course we can discretize this and rewrite this part as the following. We know that minus gamma b, can we write partial phi partial x at b in terms of p and the boundary value? We can. So that will be how much? Phi p minus phi b upon delta x b, right. That is what we have, equals h times phi infinity minus phi b, okay. Now the idea here is that if you discretize the P cell, what are the dependent variables you are going to get? You are going to get the dependent variables for phi east, right, phi north, phi south, and if you discretize it here, you would probably get in terms of phi b as well, right, if you discretize for this P cell. Now the idea is, let us not have phi b in picture, okay. Let us try to get rid of phi b and let us have a dependency on phi infinity, okay, and of course on phi p, right. You will have phi p which you will calculate, and then we want to have dependency on phi infinity, okay. So we want to get rid of phi b. As a result, what we want to do is, we want to obtain an expression for phi b in this from this relation, okay. Can we obtain a relation for phi b in terms of phi p and phi infinity? Yes, we can. Okay, so that's what I'm going to do. So that would be how much? That would be phi b times h is what I have here, plus gamma b upon delta x b, right? That's what I have, equals h times phi infinity is what I have here, and then plus gamma b by delta x b times phi p. Is that algebra correct? Okay, so essentially we got an expression for phi b. So phi b is h times phi infinity plus gamma b upon delta x b times phi p upon h plus gamma b by delta x b. Okay, so that's what we have for phi b. Okay, now what we said is we want to get rid of the dependency on phi b. So we have to substitute this phi b back into where? Into the diffusion flux, right? So essentially I'm going to substitute phi b back into the definition for diffusion flux that we have here, okay? Because in the discretized equation we don't want a dependency on phi b, we only want it in terms of phi p, east, north, south and phi infinity, okay? So, so this is the discretized expression, so I'm going to substitute for phi b in this, okay? So what would that read like? Essentially the discretization is minus gamma b partial phi partial x b, right? That would be your west phase flux, which is nothing but minus gamma b phi p minus phi b by del x b, and I'm going to replace phi b here with what we found from here, okay? Essentially in terms of phi p and phi infinity. Okay, let's do that. What would that lead to? That would be minus gamma b times phi p minus, I have a bigger expression here, h phi infinity plus gamma b by del x b times phi p upon h plus gamma b by del x b, right, divided by delta x b, right? That's what we have. So if I simplify this further, what would that be? Minus gamma b times, what do we get here? What gets cancelled? Gamma b by delta x b times phi p is a positive here, and there is a minus here, so gamma b by delta x b times phi p, this gets cancelled, okay? So what remains here is what? h times phi p minus phi infinity divided by delta x b times h plus gamma b by delta x b, right? So this denominator still remains and gets multiplied with this guy. That's what we get, right? So here we can rewrite this as minus gamma b by delta x b times h upon h plus gamma b by delta x b times, okay, what do we have here? We have phi p minus phi infinity, okay? So I'm going to get rid of the minus sign here. Then I can rewrite this as what? Phi infinity minus phi p. Is that correct? Essentially the west phase flux gamma b partial phi partial x b we have written in terms of completely in terms of phi p, the dependent variable at the cell p, and in terms of phi infinity, right? So phi infinity is the free stream scalar value or the temperature value, okay? Correct? Okay. Now let's call this coefficient that we have here as a constant. Okay, let's call this as some constant. So this is some constant k times phi infinity minus phi p, okay? This is your discretization for minus gamma partial phi partial x b, right, or minus gamma b partial phi partial x b, right? That is your k times phi infinity minus phi p, and what is k? K is your gamma b by delta x b times h upon h plus gamma b by delta x b, right? That's what we have. Now what do we have to do? We have to basically substitute for this expression back in the discretized flux equations, right, and substitute for the other values on the east, north and the south, and then collect the terms, right? That's all we have to do. So if we go back to the discrete equation, so the equation we have is gamma east A east, right? That's what we have. So A east is basically delta y partial phi partial x east minus gamma b partial phi partial x b times delta y plus gamma north delta x partial phi partial y north minus gamma south delta x partial phi partial y south plus SC plus SP phi p times delta x delta y equals 0, right? That is what we have, in which I am going to replace, I am going to use linear profile assumption for all these quantities, right, for the partial phi partial x on the east, partial phi partial y on the north and the south, and we are going to replace this quantity minus gamma b partial phi partial x b with what we just obtained here, right. We are going to write k times phi infinity minus phi p, right, and then collect the terms. So, if we rearrange in the AP phi p style, that would be AP phi p equals, if I kind of write it in a short form. So, this would be sigma A and B P and B plus B, where NB goes on east, north and south. Okay. All right. Now, what would be the coefficients? That is the question. Now, if you take a look at this one, where will these contributions go? Where will minus k phi p go? So, we have a minus k times phi p, right, this term. Where will minus k go? This will go into AP, right, it will go into AP. Where will k phi infinity go? It will go into the b term, right, because this is known. Okay. So, there are two contributions, one going to the right hand side, one going as a coefficient to AP. Of course, we have this multiplication of delta y, okay, that I have not put here. So, this gets multiplied with delta y, right. This is only an expression for gamma b partial phi partial x times delta y. So, essentially the coefficient that will go will be delta y minus k delta y. It will become plus, right, because we are sending the p terms to the right hand side. So, k delta y will go into AP and k phi infinity delta y will go into B. Okay. So, that is the contribution. Now, can you tell me what would be the coefficients that we have? So, what is A east? A east is the same as before, right, nothing has changed. So, this is gamma east delta y upon del x e. A north is gamma north delta x by delta y north. A south is gamma south delta x by delta y south. What we have is A p. What would be A p? A p is A east plus A north plus A south minus, okay, SP delta x delta y. Anything else? Plus k times phi infinity. No, phi infinity will go to the right hand side. What would go into here? K times delta y, right? K times delta y times phi p is what we got here, right? Essentially k times phi p times delta y, right? So, phi p is already taken out as a coefficient for AP, right? Then this is what that goes into the central term. Now, what is remaining? We have B term. What would be B? K into phi infinity into times delta y plus SC, okay, the source term will be there, SC times delta x delta y, right, that is all. Okay. Now, what about Scarborough criteria? Let us say we assume the source is 0, okay. If the source is 0, what is AP compared to sigma A and B? Is it lesser, greater, equal? Greater, because SP times delta x delta y is 0, but what about this guy? This is still non-zero, right? So, this term is there. So, as a result it will be greater, okay. Assuming that there is a convection happening to the fluid, okay. Now, okay, what about so and in case the source term is not 0, then anyway it satisfies Scarborough inequality, okay. So, that we anyway understand. So, essentially it satisfies in inequality. Now, do you see why it is actually satisfying in inequality? Because mixed boundary condition has this Dirichlet component in there, right, that is the reason. Otherwise, pure Neumann boundary condition does not satisfy in inequality, it only satisfies in equals, right. Okay. Questions till now? No? Clear? Easy? Okay. Very good. All right, let us move on. Then what I want to discuss next is the extension to 3 dimensions, okay, 3 dimension diffusion. That is very straightforward. We will not write down the equations, rather I want you to kind of think in your brains and then tell me, kind of dictate, and I am going to just write it down, okay. That is the 3 dimension extension. Then that will be done quickly. Then we will look at interpolation of the diffusion coefficient, right. We have this gamma that we have to calculate on the faces. Up till now we have kind of postponed it. We said somehow we know gamma on the faces, okay. But how do we actually calculate it, and which methods will give correct results and which methods do not, that is what we are going to do after the 3 dimensions is done, okay. So then the next thing is diffusion, or rather steady diffusion in 3 dimensions, okay. Steady diffusion in 3 dimensions, okay. The governing equation is the same, that is del dot gamma grad phi plus S phi equals 0, okay. Here your del operator now has all the 3 components, I dou x, j partial y, k partial z, right. That is all we have. Of course, our domain now looks little more complicated because we are dealing within 3 dimensions, okay. Let us say that is my P cell, okay. Let us call this is my P cell, and x is in this direction, y is in this direction, and z according to the right hand thumb rule we have in the top direction, okay. Then what about the neighbors? So this is the P cell, and we have one neighbor here, another neighbor here, and the north and the south neighbors, and we have of course the top and the bottom neighbors, which we are not drawing all of them, rather this is your east neighbor, west neighbor, north, south, and we call this as top and bottom, okay. So we have all these neighbors. Then we have of course the faces. What are the faces? This is which face? East face, okay. So this is your east face. Similarly you have the west face, the north face, south face, and top and bottom faces, right. We have all these faces. Okay. Now what do? We again integrate the governing equation on the control volume, invoke Gauss divergence theorem, convert the volume integral into a surface integral, then replace the surface integral with a discrete summation, right, assuming that the gradient, the diffusion fluxes remain the same on the faces everywhere, and the phase centroid value can be used to integrate, okay. We do all that, and then we kind of come for the final discrete equation. That would be what? That would be gamma east A east partial phi partial x east minus gamma west A west partial phi partial x west. Of course, you are going to get now how many terms here? 6 terms, because you have 6 faces. So that is rather very straightforward. Gamma north A north partial phi partial y north minus gamma south A south partial phi partial y south plus gamma top A top partial phi partial z top minus gamma bottom A bottom partial phi partial z bottom, plus you have SC plus SP phi p times delta volume, that is delta x delta y delta c, okay. Delta x delta y delta c, which is nothing but your if I were to draw, this is your delta x, this is your delta y, and the height here is the delta c, right. We have all these things equals 0, right, equals 0 is what we have. Okay, now it is very simple, we do not have to write all of them, rather I want you to kind of tell me what would be A east. What is the area vector that we have now? This is A east. What would be the area of that? Delta y times delta z, that is all, okay. So essentially we have delta y delta z. Similarly A west is also the same, right. Only thing is the direction is different, it will be minus I. What would be A north? A north is the back face, right? It is that guy. That is how much? Delta x times delta z, okay. So that is delta x delta z, and what would be A top? That is this surface delta x times delta y, okay. So we have all these things, then we can plug all these things back into the discrete equation for fluxes, right. And what about partial phi partial x east? Would it remain the same or it would be different? Same, it will be phi capital E minus phi p upon delta x e, all those things, right. So essentially if I were to write partial phi, sorry, okay, so partial phi partial x east is phi east minus phi p upon del x e, partial phi partial y north would be phi north minus phi p by delta y north, and similarly we have now what is the extra, which is partial phi partial z top would be phi top minus phi p upon delta z top, right. That will be the extra one, and of course you have the partial phi partial z bottom, which is phi p minus phi b upon delta z bottom, right. We have these expressions which you can easily do and essentially plug all of these back into the diffusion equation, right, into the diffusion equation, and then collect the terms, right. You will get a linear algebraic equation, okay, which is very straightforward compared to the 2D. All we get is again A p phi p equals sigma A and B phi and B plus B, where now NB goes from where? East, west, north, south, and top and bottom, okay. And what would be your AP? AP is sigma A and B, right, where again NB goes from east, west, north, south, top and bottom. Anything else in the AP term? Minus SP delta x delta y delta z, okay. And what about B? The constant part of the source, that is SC times delta x delta y delta c. That's all, right. We just have two more extra terms because of the two more phases that we have, fine. So this is rather straightforward. Now all we have to do is we have to write these equations, one for each cell, apply the boundary conditions, and then you can of course use Gauss-Seidel. Can you use Gauss-Seidel for 3D or no? Yes, we can, because Gauss-Seidel doesn't care, right, whether you are in 1D, 2D, 3D. All you have to do is go from cell to cell, right. Every cell you need an equation, and as long as diagonal dominance is there, Gauss-Seidel will be guaranteed to converge, right. So essentially you can of course use Gauss-Seidel. It will be slow, right, because if you have, let's say, 10 cells in each direction, you have 1000 cells in total. So Gauss-Seidel will be much slower than the 1D cases you have solved, but nonetheless you can use Gauss-Seidel, okay. In the coming lectures we will see an alternative that can be used instead of a Gauss-Seidel, which will be much faster than it, okay. Questions till now? So now we can kind of solve for structured Cartesian meshes, like we can solve the diffusion equation on it in all the dimensions, right, for a source term, for all sorts of boundary conditions that can be given, okay. Okay, let's move on. Fine, then let's move on to this topic, which is calculation of the diffusion coefficient on the faces, okay. That is basically how do I calculate diffusion coefficient, that is basically interpolation of gamma f, right, that is your diffusion coefficient on the faces, okay. The idea here is that, let's say if you have a composite material, okay, or what you have is you have the thermal conductivity or the diffusion coefficient as a function of space. For example, gamma is a function of x, y, z, okay. That means depending on where you are, you have a different thermal conductivity. You could have a composite material, okay, in which two slabs or multiple slabs are stitched together. In such cases, how do I calculate gamma on the faces, okay, that is the question, okay. So essentially, or you could think of as a conjugate heat transfer problem as well. What is a conjugate heat transfer problem? Might have been aware of. Essentially, you have a convection, you have a solid and a fluid, and you have to solve for both of them, right? Essentially, you have the heat is being exchanged between all these things, okay? So that's a conjugate heat transfer problem. So, in all these cases, you end up calculating gamma on the faces, okay? And then how do we calculate it is what is the question. Now, of course, what we say is that we know the gamma values on the cell centroids. That is what we are starting off with. Okay. For example, if you have a slab, you know what is the gamma value on the cells of these cell centroids. Okay. So, we know gamma on cell centroids. Okay, diffusion coefficient. Now, how do I interpolate these gamma on the cell centroids to gamma on the faces, right? Such that I can use it in the discrete equations. Fine. All right, let's move on. Let me consider a steady one-dimensional situation, okay, to simplify things, and also steady one-dimensional, and then there is no source term. Okay, let us consider all these things. There is no source, and we are looking at a steady diffusion, and then there is a one dimensions. Okay, then I can of course write down the discrete equation. Before that, I want to look at the cells. Okay, so the cells are like this. Let's say this is my P cell. Let's say the cells are not uniform. The P cell is bigger than the yeast cell. So I have this as my yeast cell. This is my P cell. As a result, the delta x I have, I would like to call it as delta xp. Okay, this is the cell width of the P cell, and delta x capital E would be the width of the yeast cell. Okay, similarly, width of the West cell would be delta x capital W. Okay, that is the cell width. This is not uniform anymore. Up till now, we have used delta x to denote the cell width for the P cell. Okay. Then of course, we have one more distance. What was that? Distance between the cell centroids, right? This is how much? Del x E. Okay. This is del x E. Now, because it is said that gamma is known to you, it will be given to you, right? It is a material property, so it is known at the cell centroids. So, we know what is gamma at on the yeast cell. This is gamma E. We know what is gamma on the P cell, right? The question is, how do I calculate gamma F from all these things that I know? Okay. Okay, of course, you can use linear interpolation. Right, and write gamma F as gamma on the face as some coefficient, that is, let us call it as Fe. Okay, this is a some factor, the linear interpolation factor Fe times gamma P plus 1 minus Fe times gamma yeast. Okay, so I have essentially Fe times this gamma P plus 1 minus Fe times gamma yeast, where Fe is my ratio of the lengths that I have. And what are those lengths? Those lengths are this length to the total length, right? That would be Fe is what I have. Okay, so that means I can write my Fe as what would be length of this guy, that is denoted with 1. That is half of the cell width, right? So that is delta x by delta xe by 2 divided by what would be the length of the second segment, delta xe, okay. So that is what I have. So this is my Fe. Now essentially I am forming a fraction of 1 to 2, right. So that fraction times gamma p plus 1 minus that fraction would give me which one? It will give me a ratio of this to this, right. That fraction times gamma e. Is that correct? I am taking the arm lengths, right, accordingly, and I have formed a linear interpolation, right. Fe times gamma p, that is on the left hand side, and 1 minus Fe times gamma e, that is on the right hand side, right. Fine. So this is linear interpolation, very good. Then of course, if the phase f is halfway, let us say if f is midway, then what would be, if f is midway between these two, then what would that mean? That is half, that is coming because your delta x capital E equals delta x small e, right. The width of the cell is same as the distance between the cell centroids, right. Only then if it is halfway, that means essentially we have delta x capital E equals del x e, then what will this ratio be? Half, right. Delta x e equals del x e, you have a half remaining, right. So this will be 0.5, that means we are looking at midway interpolation. Then what will be gamma f? Gamma p by 2, fe is half, plus this is 1 minus half, that is again half, this is gamma east by 2, then we get our arithmetic average, right, gamma p plus gamma e by 2, this is our arithmetic average of both gamma p and gamma e. Okay, we have not done anything great, we have just rewrote arithmetic average and a general equation for it, right, in terms of calculating the gamma f. Now, of course, can I use this formula? You can, but it appears if you use a arithmetic average, okay, this leads to incorrect results, okay, in some situations, okay. So in some of the situations we will not be using a arithmetic average. Now this is what I am kind of claiming, we have not yet proved, we will prove it in a little while, okay. Rather we use a slightly different approach. So we use an alternate approach with somewhat simple like this method only to calculate gamma f, okay. That will give better results under all circumstances, okay. Okay, now I have just claimed something here, okay, we have not yet proved, we will prove it in a little while. What I said is, okay, if you use arithmetic average or just linear interpolation, it may not give correct results, it will give incorrect results in some situations, which we are going to see, okay, especially if we have gamma as a function of a space and if we have a composite material and things like that. Rather, if you use an alternate approach, then the gamma f you would calculate with from an alternate approach would give you better results, okay. Now this is a claim we are making, which we will prove now. Before that, what it seems is like we are actually, the question we have to ask ourselves is, we do not want to calculate, the question is not how we calculate gamma e or gamma f, okay. This is not the question. The question is, the correct question is actually how do I model the heat flux that is going in through the phase correctly, okay, that is the question. And if you can correctly calculate QF, then the resulting gamma f would be the gamma f that you would need, okay. This is what you would get, which would give you the correct heat flux through the phase, okay. So the question is, how do I calculate heat flux correctly such that heat flux calculation terms, the gamma that whatever is kind of appearing there would be the right gamma I should use, okay. So that is the question we ask ourselves, okay. So with this I am kind of going ahead and then I will redraw what we have. Essentially we have, let us say, a composite material. So this is my P cell, this is my east cell, okay, this is east, this is P. Essentially this is of different thermal conductivity or different diffusion, and similarly this is of different thermal conductivity, okay. So essentially what we have is gamma east here, and with what we have here is gamma P, okay. So these are two different materials and we have to calculate what is gamma f here, that is what we have to do. And then of course we know the distances, this distance is del x e and this distance is delta x e by 2, this is delta xp by 2, right, that we already know. Now, you have heat flux that is going this way, right, this is your Q, let us call it Qf, right, that is the heat flux that is going through this. If I were to represent the temperature values or the phi values at the cell centroids, where would that be? They would be here. This would be how much? Phi capital East, and this would be phi capital P, right. So, what we want to do is we want to essentially calculate the heat flux, right, that is Q East would be some gamma East times phi East minus phi P, right, divided by delta XE, right. Of course, there is a minus also, here, right, this is minus gamma East phi East minus phi P by delta XE, right. Let us call that equation 1, okay. Now, if I were to draw an equivalent, let us say from heat transfer analysis, for a simple 1D no source and steady situation, if I were to draw an equivalent network here, what would that network look like between P and E? So, that means I have this is my P, I have some resistance, then this is my phase and we have some resistance, this is our capital E, right, and we have Q is going through this way, right, we have QE is going across this one, right. What would be the equivalent resistances that we get here? Resistances would be nothing but the thermal conductivity, the length divided by the thermal conductivity, right. We are actually looking at L by K, and the L by K would correspond to, what would be the L that corresponds to here? Would be this length, right, would be this length, isn't it, this length, and then what will be the thermal conductivity for this one? Gamma E, and the other length would be this guy, that is delta xp by 2, and the thermal conductivity would be gamma P, okay. So, can we write, so that means what is the first one here? This would be length is delta x P by 2, P by 2, and then this is L divided by K is how much? Gamma P, this is the first one. What about here? Delta x E by 2 times gamma E. Do you all agree that this is correct? Fine, okay. Now, if I were to write a expression for QE, what would that be? From this resistance network, what would be QE? So, these are in series, right. So, it will be some of these things, these are in series. So, what would be the potential difference? Phi P or E? P, right, minus phi East, is that correct? Divided by what would be the resistances? Sum of these two, this will be delta xp by 2 gamma P plus delta xe by 2 gamma E. Is that correct? Right? That is what we have from a heat transfer analysis, 1D heat transfer analysis. So, this is equation 2, okay. Now, what do we want? We want, this is the correct heat flux that has to pass through the phase QF. So, we want essentially to calculate now gamma E such that we get the same heat flux, right. So, we want to equate this QE equal to this QE, right, and then calculate what would be the corresponding gamma E, right. Then we would get the correct heat flux passing through the interface. Agree? Yes? Okay. That means let us equate these two. So, what do I get if I equate these two? P East minus P. So, there is a minus here, this minus will rearrange this thing, okay. Then if you bring gamma E down, we have del x E by gamma E, right, equals this entire thing in the denominator, right. Essentially here I have, I equate this QE from equation 1 and 2, what I get here is del x E by gamma E, this should be same as this quantity, right, because phi east minus phi p is the same in both of them, and QE has to be the same, right? Do you agree or no? Yes, okay, very good. So then that is nothing but delta XE by gamma E equals delta XP by 2 gamma P plus delta XE by 2 gamma E, right? We just equated these two, equation 1 and equation 2, right, and then found what is gamma F or gamma east, okay. That will give us the correct heat flux through the phase. Okay, now here I can of course rewrite this as gamma E minus gamma E inverse, right, gamma E to the power minus 1, as I will bring delta XE to the down on the right hand side. That would make it, I am also writing the E term first and the P term next. So we have delta XE by 2 del XE times 1 by gamma east plus del XB by del XP by 2 del XE times 1 by gamma P. Is this okay? I just brought delta XE on the right hand side to the denominator, okay. Now what is delta XE by 2 delta XE? We have defined this as FE, right, this is FE upon gamma east plus delta XP. Can I write delta XP? So delta XP is what? Delta XP is this distance, right, okay. Delta XP is this distance. What about delta XE is this distance, right, okay. Can I write delta XP plus, okay, essentially I want to calculate what is delta XP. Can I write it as 2 times delta XE minus delta XE, right. Essentially I want to add this part and then subtract off the delta XE. Can I do that to get the delta XP? Yes or no? Okay, so that means I can write this as 2 times delta XE, right, minus delta XE upon 2 times delta XE. Can I do this? Right, I can do that, okay. So this is nothing but FE by gamma E plus what would this be? 1 minus FE by gamma P with a minus will be my gamma little e, right, okay, minus 1. So this is my effective diffusion coefficient on the phase in terms of something else, okay, where of course we have defined FE equals delta XE by 2 delta XE, right. Now let us say if my interface is midway, then what would be FE? FE equals 1/2, right. So can you plug in 1/2 into this expression for gamma E and calculate what is gamma E? Yeah, so plug in this thing. So essentially what would that be? That would be my gamma little east equals 1 by 2 gamma east plus 1 by 2 gamma P to the minus 1, right. That would make it 2 gamma east gamma P plus gamma east inverse, right. This is gamma east. So what would this be? Gamma east equals 2 gamma east gamma P by gamma P plus gamma east, right. What kind of an average is this? Harmonic average, right. This is a harmonic average, not an arithmetic mean, this is an harmonic mean. We got, what we got is a harmonic mean, right, which is different from the arithmetic mean that we got before. We thought we will use a linear interpolation, okay. If the interface is midway, right, fine. Now of course we have still not proved anything, okay. We just said, I claimed that this method supposedly the harmonic mean will give better results than the arithmetic mean, right, that is what we said. And then we said if you model the heat flux instead of calculating gamma by some ad hoc method, it gives you a better result. That's all we have claimed, but we have not proved anything. We just proved that we found another expression for gamma little east, which is the harmonic mean of the two thermal conductivities that we have rather than the arithmetic mean of the thermal conductivities. So what we do next is we kind of consider specific cases and then see that whether each of these things work or not. Okay, so that's what we do next. So if I consider, let's say, a case, so let us look at some comments. Let us consider a case where the gamma east that we have is an insulator. Okay, so we have a conductor and then we have an insulator. Okay, so gamma east has a thermal conductivity that tends to 0. Okay, gamma capital is 0. That means we have two blocks and one block is conductor and the other one is insulator. Okay, if gamma east equals 0, then what would be the gamma little e that you would get from the arithmetic average, and what would be that you would get from the harmonic average? Arithmetic will give you gamma p upon 2. What would be the one for harmonic average? 0, right? Now what is that you would expect if you have an insulator, right? So the conductivity is 0, right? What is that you would expect for it to behave like? Should it have at the interface, should it have some thermal conductivity, or it should be 0? It should be 0, right? Which is kind of given by the harmonic average, whereas if you had calculated from the arithmetic average, it would have half of the other average, which is not correct, right? So this is not physically correct, whereas the harmonic average will give you the correct averaging in this case. Okay. So if you have an insulator, then at the interface we should have gamma E should tend to 0. That is what is correctly recovered by harmonic average. Okay. So there are a couple of more comments that we have to make. We will make that in the next lecture.